Hey. So I'm guessing quite a few of you have, pretty much everyone here, I've already said hello to. So I've been working working on things related to symmetry for a good while now, and this is a story of one of the things that we've been doing. And then I'm going to go a bit more into detail about ranges and why they're interesting. But first, let's begin. In the beginning, variables and functions. Pretty okay? It's fine. I don't see anything wrong with that. Just after the beginning, more variables. Still, like, I'm already looking at this and going, I'm not happy. And then there were more functions as well. And by this point, I'm really, really not happy. D trivia, you can have Unicode as your identifiers in D. You can use emoji as your variable names. Or in this case, zeta. But, so already here we can see that we've got a problem. We've got a bunch of different variables. They're called, you've got x1, x0. You've got two different functions. It's just, it's ugly. Iteration and composition is the core problem there. You have x1, you have y1, you have y2, y3, y4, you have z1, you have z2, you have a1, and then you have multiple functions that mean you need to connect them together, and that's composition. So very briefly, what a range? What a range? What's a range? So I'm just going to do very brief, the very basics of what a range is. I'm just thinking about the simplest things. So empty, front, pop front. Do we have anything? What do we have? And go to the next one. So you can imagine this can take you through a set of data one by one. And it lets us do crazy things like this, where we've taken a list of things, the numbers from 0 to 99, we've mapped them, multiplied by a random number, filter for the ones that are odd, and write the result without allocating any memory, definitely without having written x0, x1, x2, x3, x4. Dead simple solution to the problem of wanting to iterate over some stuff. And also, notably, composition, because we have map, followed by filter, followed by write line. There are other primitives for going backwards. You can get an element by offset. You can save the current position. But I'm going to skip over that for this. And C++ programmers, begin and end iterators. Gives you, it's the starting point to thinking about ranges is there, if you're used to C++. So what was our problem? Iteration and composition. We just had the same problem viewed from a different angle. So what we wanted is we wanted to allow people who are not currently programmers to do some bulk data processing tasks, because there's a lot of domain-specific knowledge that a lot of practitioners have in finance, and most of them are not programmers. They don't want to be programmers, but they do want answers to their questions, and they want answers to their questions now, not in 3 months. And if you have a process where they ask questions and they have to go to the tech team and go, hey, would you implement this for me? And then the tech team says, well, I'm busy. Is the normal response. And then they come back 3 months later and turn up, hey, look, I did it. And whoever asked the question in the first place goes, I don't care. Like I needed the answer today or never. So people need to be able to answer questions quickly. And there's also a need to glue together business code in a way that is more accessible and requires less communication between tech people and practitioners. You can get a lot more work done with a lot less talking if you don't have to explain every piece of the business logic to a programmer. So we needed something that would skip the Excel problem, which I think I'm going to not talk too much about because Robert covered that. And we also needed it to be easy to use, so people would actually use it. Hard to abuse, because see the Excel problem again. And it needs to express the thought at hand clearly, because people come and go. Programs live a lot longer than you ever think they're going to, especially when they've been built for a special purpose by someone and it's lived on their machine. So it needed to be auditable. You should be able to go look at it and see that it does what it does. And again, the audit of the code needs to be done by someone who understands the business domain, as well as perhaps by someone who understands the programming domain. But it's hard to find people who are both. So therefore, it being readable by someone who is not a programmer, very important. I mean, it's crazy, right? Why would you not just use Python? Why would you not just use something else? Why would you create your own solution for this? Programming languages is something people have been working on for ages. There's lots of good ones out there. Python's supposed to be easy, right? We'll just have people write Python scripts. I believe that imperative programming is the hard part, not the easy part. I think that starting people off by writing loops is something that clever people can pick up quite fast. But writing correct loops with complicated logic is really, really difficult. There's a lot of patterns that we've all learned because we've done it forever that people who are not programmers don't have. What they actually think about is in terms of transformations, because they've all used Excel. Excel is a functional programming language. Mutable state, if you let people change things, they will change things. They will not have discipline, right? The idea that you go, oh, it's fine, we'll just be careful. They won't be careful. They won't know the meaning of what careful is, right? And also, it just means that at a glance, to understand what's actually happening and why is this variable suddenly different, or what value does this variable have, becomes a question you have to sit and think about. You have to trace the code through. And yeah, just generally harder to reason about unless you're a programmer and you're practiced. No proper pipeline programming. So in the example I gave before, whoops, yeah, see, this is going to be the this is why you don't do that. So here, you have a pipeline. This is via uniform function call syntax. So you start with the numbers from 0 to 99. Then you map something onto it. Then you filter that, and then you write it out. The data flow follows the visual flow, and I think this is a huge win for readability. And to have that in any other system is actually, it's not that easy to find it. You end up starting to have to create types that have methods, which is like the Java streams thing, just uses special methods. Like that filter would be a member of a stream there. So you end up having to create this whole, like a framework in Python or any other language to support this sort of pipelining stuff, and it's not so easily extensible, and so on. And they weren't designed from the ground up to be trivially interoperable with all sorts of other languages and systems. But yeah, that's another talk next year. What did we do? Well, we thought, okay, you've got to make a language then. So, as we've heard already today, Pegid is, it's pretty good, and it's based on parsing expression grammars, and it's got some nice extensions. So that's where we started with. We created a grammar there, simple stuff, variable, arithmetic, array literals, and so on. Used tagged algebraic initially, then replaced by totally custom stuff now, but initially we used that to create a variable. A recursive variable type, so you have a table of variables and an array of variables that can exist within a variable. And anybody who's looked at how JSON works means that you'll notice that you've basically just created JSON. If you can do that, as long as you can do int and string, well, double and string, I suppose, add a few other details, and Boolean. And an open-ended variant type. So you can actually dump anything in it. You won't necessarily be able to access everything that is in that type, although in some cases we do support that. Very simple parse tree walking interpreter, recursively builds up variables. Eventually you've finished parsing the tree and you've finished interpreting over the parse tree, and what you get at the end of that is the result of whatever computation you were doing. And because there's no mutable state, all of this is very simple to implement. And the next step was going to be, yeah, we're going to do array operations, and it's going to be great. And then people are going to do A equals B plus C, and there's going to be arrays, and they're going to be able to write little expressions on time series. It's going to be fantastic. But then I went on holiday. and then I got ill. And then I came back. And everything was different. First-class support for ranges got added. A large chunk of the D standard library had been wrapped. A project was started to try and use the language in production in something really important, the risk reports that Laith mentioned, and that was going to have to happen starting now, not the use in production immediately, but like, get on with it. So, okay, this was suddenly felt like a different task entirely. Later on, we decided like modules, being able to do if statements. It's a nice idea. I've heard that programming languages like to have them. Scopes, not overwriting live stack frames. That was fun. We didn't have a stack for a while. When you recursed, you were back in the same function as you were, same stack. That led to some very interesting bugs. Useful features, I think. So, that's some D code. I showed it earlier. Turn it into SIL code. You can see why I used this weird D alias add thing, partly because it's short, but also because it made my translation look nicer. But you can see it's dead simple. You'd be familiar with this from all sorts of other languages. It's got arrays, and then the interesting bit. We've got map, and we're able to call functions in a pipeline manner, UFCS, exactly the same as in D, but we use a slightly different operator, which makes it sort of clear the direction of movement, the things are flowing. It's a little annoying to type, but it is what it is. And that map, that's not our map, that's just Phobos's map that we wrapped. And that's the story of really the overwhelming majority of the code that gets written in SIL is just calling straight into Phobos functions. So yeah, we cheated. We didn't want to have to write code. We didn't want to think about what code should be because Phobos has already done the work, so we just call Phobos. Yeah, we didn't have much to work with, so yeah, we just stole Phobos. So here's an example of a very simple little real piece of code. We read a CSV file, parse the dates in the date column, go by row, filter the rows that have the day of the week equal to Friday, get the close from that data point and the date, create a table from some pairs, from those pairs that map creates, and write a CSV out of the weekly closes. Dead simple, straightforward. You can read it, and it's hard to misunderstand. I feel like it's always hard when you're a programmer and you're talking to people who are not programmers, trying to work out what do they know, what can they understand, which statements are trivial for them to understand, and which statements are an absolute nightmare that they don't even know where to start with. It's the same as the other way around, by the way, when they ask you to do something, and they don't seem to understand the difference between something that's going to take 3 months and something that's going to take 3 hours. So at the beginning, we really didn't have much in the language. Things moved very, very fast. We didn't have any table literals. We just hadn't put them in the grammar. And we were in a rush to start implementing things. Didn't want to have to do a turnaround of going and messing with the grammar, having to think hard about that. We were busy writing out code in the language. We only had something that created an empty table and add entry. So you go, oh, this is going to be awful. But then this table from pairs thing turned up, and that was just used fold. You start with an empty table, and you fold in new entries from a range of pairs at the beginning, right? Horrible hack? Well, maybe, but I was able to write that pretty quickly as soon as I needed to, and work continued. Super secret hedge fund table was generated. And you can see it's just the same thing as before. We got an array of pairs, and then we pipe it to table from pairs, and that's just as if it was UFCS. Didn't have any built-in functions that operated on the values of a table. We had this idea of a table, but we didn't really know, you couldn't really get into them very well. So we wanted to apply something to every single element in a table. It's exactly the same thing, we just used fold. And again, this is Phobos's fold, we didn't write a fold. You start with the table, you go over key value pairs of the table, which is a function we did have, although we don't anymore, things have changed. But we do, you start with the table you started with, and you replace the entries with the application of the function to that entry. Dead simple, and you can see at the bottom, this is, by the time we did have table literals, this one, starting with the table literal, which you can see is basically Python's dictionaries. Apply the transformation to every variable, every element in the table, and 3 goes to 6, 4 goes to 8. Dead simple. No proper data frames. Yeah, nobody, anyone in symmetry will be glaring at me for this. But no problem. Okay, still a problem. But not as bad a problem as if you didn't have ranges. You want to get one row. You just get a table. You pull the keys out. You pull the values out. In, zip, over going from each, with zip to go to a pair of the key, and map the value to the first element, and give that to table from pairs, and you can get a row. Bang. Is it efficient? No. Does it pain me that I actually wrote that? Yes. Yes, it very much does pain me that I actually wrote that. But on the other hand, I was able to do it in a couple of minutes, and we were able to carry on working and get closer to the goals we actually have. Don't be too clever. Yeah. So we didn't have, so in this slide here, we had this idea of a local, k's, v's, and then in, it's like let these be this in this expression. Didn't have that for a long time. So you start thinking, you start going, oh, I know how to do this sort of thing. So you have a function which takes a variable, and then you call that function immediately with a calculation. Oh, horrendous. Interestingly, some people really picked up on this and went, yeah, that makes perfect sense. Notably, some people did not. And I think they're right, and they should not. If you pick up on this, you're pretty sharp unless you're a programmer, unless you're like a full-time guy. So, yeah, we fixed that. Declare locals, use them in the expression. Much more readable. You don't have to work inside out. You just get to work forwards. I think that's one of the key things that I've been focusing on in the language, is that you should be able to work forwards from the beginning and understand what's happening. Okay, so that is the end of my little bit about what we've been doing with ranges in symmetry. We've had a very good experience with them, I have to say. It seems that people who are not programming experts are able to understand ranges pretty fast. And understanding these functional transformations on data, they've been doing it forever in Excel. It's really not any different. They're just writing it as opposed to click and drag and typing little formulas in cells. And people do like being able to see the code out in front of themselves. It's one of those things where I think people don't realize what they're missing until they can see the alternatives. And as soon as you show it to them, they go, okay, yeah, I can understand what the code does, as opposed to clicking randomly in an Excel spreadsheet, hoping to find one of the formulas that will explain what's going on. So now I'm going to move on and talk a little bit about ranges themselves. This is when it gets a little less casual and a little bit more me moaning about things. There are positives and there are negatives here. So, can anyone tell me what is wrong with that? If I'm correct, it compiles. And it does what it says. But what's wrong with it? Why would I not like to use this function? Any ideas? Well, let's say that R is a no-GC range. Let's say that multiplication is no-GC. Let's say that copying T in by value copying, the range in by value, is no GC. Can I put no GC on this? No. Why can I not put no GC on it? Yep, there's a closure over V. And this is something that pops up again and again on the forums, in conversations. I've been thinking about it for years now, and it's really annoying. And the easy place your mind goes to with this is you look at C++ lambdas, and you go, they can capture by value, so it's fine. That actually, it turns out, is completely missing the point. It's really easy to capture a variable by value and create a callable out of it indeed. That is not a difficult thing to do. It's just a struct with an op call. You just create a struct, you put the V in it, you put an op call on the struct, bang. That's completely equivalent. The problem is, it's a problem with map, actually. And it's a problem with ranges in general. Not the design of ranges, but the way that all of the ones in an STD algorithm actually work. Well, not, maybe not all, but pretty much all. That lambda is an alias parameter. Let's say we captured V by value. Where would that value be stored? On the stack. Whose stack? Because it's on this stack right now, but then you return it, and that's a closure. So there'd have to be some space in map for it to be stored. But how does it know that? It's just got an alias to a thing. So this is actually a fundamental problem with doing things with alias ranges. And no amount of thinking really hard about how to do capture by value lambdas is going to solve your problem. I tried, I thought a lot about it, and I realized that I was just going the wrong direction. So let's fix it. This has been talked about on the forums. People know the fixes. Well, okay, let's see the things that don't work. So here we create the struct. We put the value in the struct. That's that callable x. Oh, sorry, that should be callable v. And sure, we've created something that captures it by value. But then we do map bang c, an alias to c, a local on this stack. Still a closure. Okay, cool. Well, let's say, what do we do to fix that? Well, we just put it straight in, right? I don't want to refer to the stack. That's fine. Well, that doesn't compile. That definitely does not compile, because that's an alias to an expression. And again, there's got to be some storage somewhere. Now, it's possible we could think about how to do aliases to somehow introduce some storage space in the template that's being instantiated with the alias. That's a bit beyond my language capabilities, I think, language design capabilities. Okay, so we do a static callable. Great, now it's not on the stack anymore. Fantastic. And this, now you can make that no GC. It's completely fine. Works. Yeah, it doesn't work. Because you create two ranges, and the second time you change the static variable, and it doesn't work. So then you go, okay, you're going to start asking questions like, maybe I can be building up an array of static. No. So this is what you do. Okay. Nobody can be happy about this, right? It's really smart, but it does not scale. It does not scale with many different variables that you want to put in and chaining things and integrating things in different parts of it. You have to plan up front all the things you want to zip in, or you're going to have to do an awful lot of manipulating of these tuples appearing and needing to be broken down again. There are some clever tricks that I'll get to a little bit later that make this a little nicer to look at, but still, it's miserable. It's pretty clever, though. You just have an infinite range of V that is accompanying your input range, R, and then you just work over it in lockstep. The second element of each tuple that you get after the zip is just that constant every single time. And actually, the compiler does a pretty good job of generating good code from this. It's not perfect, and one of the things I really don't like about this is, in this case, it generates good code. Once you start doing lots of variables with this, code quality really, really starts to drop. I'm not sure if that's a fundamental problem. Maybe it can be fixed, but yeah. So what are ranges bad for? They're good at walking, but they're not good at wandering. They're really good at going from the beginning to the end of something, or the end to the beginning of something, or to a specific point. What they're really bad at is wandering around something because of the admittedly very good design decision of they always, slices always shrink, ranges always shrink. But when you compare it to iterators, where you can move you have a beginning and an end, and then a third one that can wander backwards and forwards. And I think some people have had an experience of trying to improve some of the, I think it was in SCG Container, there was some range-based stuff that you just could not do it efficiently with ranges. You really, really wanted to have 3 iterators. A pair of ranges is a solution that works, I think, some of the time. I haven't dug into the detail there, but some people definitely have, I remember. Good performance is reliable when the code is trivial. Theoretical savings, practical catastrophes. I'm being melodramatic. It's not catastrophes. But when people write range-based code and they're not programmers, it's very easy for them to accidentally end up recalculating everything hundreds of times. N squared, n cubed, n to the 4. It's not hard to get there with ranges if you're not careful about when you actually store things into arrays. Dimitri has some clever tricks up his sleeve that will maybe solve some of that problem for us in SIL, but in general in D, it's very, very good, and then you get it wrong, and suddenly you wish that memory allocation and copying was your problem, because compared to ranges re-evaluating each other, it's nothing. The thing that really bothers me about ranges is that it's really interesting to write ranges. When I write a new range from scratch, I find it a fun programming problem. I sit down and I think about it, and I go, oh, so this is going to, so then I pop front, and this changes, and then, okay, am I going to have a Boolean? Let's try not to have a Boolean flag that keeps track of whether I've calculated something. It's way too interesting. You know when it's got too interesting, you've gone wrong. It needs to be simple and easy to do. So then, this is not a new idea. There is a function which I somehow didn't know about until I randomly ran into it earlier today while finishing my slides. Luckily, it didn't change the message of my talk too much. SCG range generate. Who here has actually ever used SCG range generate? Okay, that's pretty good. That's pretty good. Yeah, it is. It's a nice idea. Yeah, it's pretty cool. I didn't know anything about it until today. Effectively, it lets you write an infinite range from a little lambda, basically, from a delegate. It's smart. But it can't skip, and it can't stop. The only thing you can do to stop it is to change some other range on the end. All the examples have like take 10 plugged on the end, or until something, right? So you didn't really write a range, you just wrote something that spits out numbers forever, or spits out things forever. That's not really the same. And it doesn't really have the capacity to take an input range, sorry, that's going to be a confusing thing to say, take a range as input and skip over some of them. So implementing filter with it is not good. So I wrote a thing a month ago, before I didn't know generate existed, where it's ugly and it's weird, but that is, and it's only like forward range, it's only input ranges even at the moment, but it enables you to write this code. So I implement just the forward range version of map without ref, But then I think most of the time that's not what you care about. Mostly ranges are used for the data goes in and the data comes out the other side. So this is just a function that seems pretty sensible. If the input's empty, stop. Otherwise, return the value of the front and pop it. Pop the input range. And that works. That just gives you map. Now, people who maybe just have a good aesthetic sense will be looking at this and feeling pretty unhappy, because what is that monstrosity on the right-hand side doing in what should be something easy? Come talk to me later over a beer. It's miserable, and it's to do with implicit conversions, and I'm not going to go over it in this talk because I don't want to make everyone too sad. So here's filter, slightly more sophisticated. If the input's empty, return stop. Otherwise, I'm only doing this in front thing just because reading front can mean calling the front of, say, map, which calls the lambda, and that is exactly how you end up with accidental n-squared problems with ranges, is when you don't cache front. And then I do if the function is true, then return the value and pop the range. Otherwise, I return nothing and pop the range. And this all works by this S, this hidden in here, is the iteration state. So every instance of this function is called on the iteration state. So it's effectively a cumulative fold. It's like a very special purpose and actually slightly generalized cumulative fold function. But it does mean that you can start writing ranges in line in your pipelines using simple to understand code, normal logic. Now, the alternative to this that most people would think of would be using some sort of generators. So you're using like fibers, you're going to yield a value. And that's great. I think that's amazing. But we don't have first-class support for that in D. There's inline assembly to make it happen, if I remember correctly. I think that was true. Maybe people have made some improvements, but the performance isn't that great. And it's kind of unfamiliar, the idea that you can yield and then you're going to come back to that position again. Whereas here, this is just straight line code. Like everybody who knows how to write code in D, they can just write that. They have to follow the rules, like they have to know that they need to pop the input. By the way, this pop input is something that takes the iteration state and returns the iteration state. Value is actually a member of S. That's what that with S is doing. And it takes the value that the next front is going to be and returns the iteration state. So this whole thing is about taking the iteration state and moving forwards. Oh yeah, this is nonsense. Chunk by. Now this code is up on GitLab. I have a MISC repository which has things in it, and there is BetaGen in there. If anybody can work out a way to do chunk by with this, that'd be really cool. If you think this is vaguely interesting to you and you want to see how far it goes, the way to learn really fast is to try to implement chunk by using it, and you'll soon see where all the ugly things happen. Particularly this comment here is there for a reason. Something goes there. I don't know how to work out what that something is, and that comes from implicit conversions, which I'm going to skip over for now. If I have time, I'll come back to it. So now something just more general about iteration. So commonly people talk about internal iteration and external iteration. That's a popular thing. Some people might not be familiar with it, so I'm going to go over the basics. The iteration happens inside the code of this for each. That's a JavaScript for each that prints 1, then 2, then 3. The iteration happens inside for each. For each is a member of array, or whatever it is in JavaScript. Yeah, the iteration happens inside for each. Sum, in NumPy's sum, right? The iteration happens inside sum. Sum has a loop in it, loops over the things, calculates the sum. Op-apply in D is internal iteration. The iteration happens inside the op-apply, or in this case, I suppose, no, it is inside the op-apply. For each is not actually iterating here, op-apply is iterating. You can see this for each in here is doing the work. So that's internal. Everybody's familiar with that. Everybody's written loops. External iteration. Iteration happens outside a pair of iterators in C++, right? You have begin and end, and you move them around, right? That's you doing it. You're moving it. So that's outside, external. Generators in Python. The iteration happens outside the generator. A generator does not iterate. It can be iterated. A range of directory entries in D. A range, it's external. You can look at the front and then you can tell it pop front, and that moves the range forwards. And actually, it's the same in SIL. We didn't just steal the ranges code. We stole all of Fables. So directory entries, it's exactly the same. Suspiciously similar. So which is this, though? Is this internal or external iteration? Well, you kind of realize that the abstraction doesn't really work. It's not actually a very useful way of talking about things, I don't believe. Because they're obviously both. The loop is iterating, the iterable is being iterated, right? This code is internal and external iteration. Both of those, internal and external iterations, are merely the description of the two sides of iteration. So, internal, sure, I know how to iterate over my stuff. I even know some different ways. Just tell me what you want done and I'll make it happen. When you know everything you want to do, it's fantastic. External, no idea what you want. Don't even try and explain it to me. Just tell me what you want and I'll spit out the next item for you. It's composable. You build up the work in pieces. Internal, I iterate things. External, I can be iterated. Most ranges are both, actually, because most ranges are things that apply to another range. So they iterate the source range, but they are iterable. So the internal aspect is trivial for map, right? Map, when you pop front on map, it pops front on the internal one. So that's not particularly interesting. But for filter or cache, when and how much the input range gets iterated is pretty variable. So in a way, there is a good deal of internal iteration happening in filter and cache. But like, who cares, right? This all just sounds like this is just semantics, right? I've come up with two terms and I've defined them and then gone, they're not very good. Well, that's not very interesting, is it? Well, it turns out it's actually key to a lot of what makes D good and a lot of what makes ranges good. Internal iteration is a closed model. You iterate and then it's done. You do the work and it happens. External iteration is composable and open because you are offering an interface to the world that says, I can be iterated, and someone can consume that and offer another open interface and go, I will iterate with some modification. So you get to compose different pieces together. It's the same thing as many things in D. You allow choices to be pushed further and further up the call stack. This is something that we've been seeing across everything in D. It's all like put allocators in the interface to let people choose what they want to do, or pass a delegate in that receives elements as they're served up, like how one of the overloads to string works. It's also the Unix philosophy, fundamentally. You do one thing and you do it well. You take the world as it is and you make a transformation to it. And you move the world forward, but you move the world forward in one way. And everything else is someone else's problem. This is actually why I think the Unix philosophy is popular amongst programmers. I think the better the programmer is, the more they're likely they are, or at least the more stereotypical the programmer is, the more likely they are to like the Unix philosophy, is because they like to have their little space where they do things, and other people's problems are not their problems and are kept at a really safe distance. How many things does this function do? I'll accept answers. Someone, how many things does it do? In a Unix philosophy sense, how many things does that function do?
Maybe 3 or 4.
Yep. I'd say, I'm going to say 3, because I think input check is fine. Like, I'm not upset about input check. I think that's, validation doesn't count as using up your, your quota, especially when it's debug mode only validation. So it creates an array, it multiplies the elements of the array, and it stores the elements. It stores the results of those multiplications in the array it's just allocated. So that's 3 things. Vecmul, 3 things. So clearly not very Unix philosophy-y. If you're working in NumPy or something, that means that your multiplication operator is no longer very Unixy, and this doesn't feel good. How many things does this function do?
2.
Yep, 2 things. You passed in the buffer, so it doesn't allocate the buffer anymore. You pushed a choice up to the user. Now, I don't care for this. This is how, this is effectively one of the level 1 BLAS functions with a different name. It's fine, right? But no one's going to get excited about it. How many things does this function do? I say this does 1 thing. Oh, I forgot that I put in this here. This was just as an interesting little thing that makes life a little bit more pleasant for this whole thing of zipping things. and then doing operations on them. This is taking the tuple and renaming the elements of the tuple. So as then when you use them, oh, sorry, that should be p.la and p.lb. My mistake. Yep, sorry. So this does one thing. It multiplies the elements of these input arrays. That's all it does. It doesn't put them anywhere. It doesn't allocate any memory. It just does one thing. So I would say that's deserving of being called a sort of Unix philosophy function. And you've actually pushed all the choices up to the user. They can choose where they want to put this. They can choose how much of it they look at. They can choose how if they're going to allocate memory for it, they have complete control over it. Now, obviously you go, well, that's just making more work for me. I want the function to do work. But yeah, but you just put .array on the end of it and give it a different name. And then sure, you can go back to your non-Unixy function that is, but I would prefer if you called it what it is, which is multiply two vectors and put the results in a newly allocated array. So it's kind of clearer what you're doing. Okay. That is an unexpected, there we go. This effect is fractal. This should happen at every scale. There is no point in your code except at the top level where this composability and allowing things to bubble up the stack should happen.
Should happen outside of code as well, for pull requests and commits and stuff. I'd like to point out, and we discussed that I think yesterday, you don't want to limit that to code actually. You want to bubble it upper in the toolchain during the code review process and all of that, where each patch does one thing and only one thing, and the tests that come with it is part of the thing.
Absolutely. This whole approach goes much higher than that. Yeah, definitely. So, okay, got a little bit of time left, so I might get into a couple of little extra things. Let's see. What if with was an expression? Wouldn't that be cool? So people who pay attention on the forums or look around at D projects have seen this expand thing pop up in various discussions. I can't remember who the original author was, and when I went to try to find it in the forums today, I couldn't find it. Effectively, it takes a tuple in, because this enumerate passes a tuple of index and value, and it expands that out and passes it as two variables, which I've chosen to call them index and value, which matches what they are in the tuple. But there's no reason why I had to choose that. But it does mean that I had to say index value goes to index plus value. What if with was an expression? Sure, you can do this already if you build a bigger lambda and you go with this, open your braces, return the result. But I think that would be nice. And there's other benefits for it as well. Often when you want to use a with expression, you want to declare variables in a with, but with defines a scope. Irritating. So if it was an expression, you'd actually be able to have the name of the expression with and then the expression you want, and it would simplify quite a few cases. And it would remove the need for things like expand, and it would remove the sort of stuttering index value. And it also means that you encourage people to use names in their types that are meaningful. You saw the rename that I used before, which took a tuple that previously just had no names and added names to it. I think that's really, really good, especially when you start getting into things with having proper debugging support, because then when you look at things, you actually get to see what name they have. Mike, please.
All right. We've been discussed this on IRC many times, and I think somebody pointed out that there is a pull request for this somewhere. I was searching for it, couldn't find it. But maybe this should be something highly prioritized in the to-do list. So Andre, Walter, this is extremely important. I mean, for me especially.
Yeah, it's something I've missed from very early starting to work with D. I mean, I can't even remember what I've been like writing in D for 6 years, 7 years. And I think by the second year, I was really missing this. And the thing is, it's a hard to argue feature because there's not actually, it doesn't really do much.
It's useless.
It's completely useless and pointless, but you really want it. It just makes life more pleasant. Okay, so that's the end of my talk, I suppose. But first, come work at Symmetry, please. Now, please. Thank you.
Questions. Get your questions up. Up the back there, Stefan.
For that width thing, so I'm not a language designer, but just from an implementation standpoint, this strikes me as quite problematic, and I can't put a finger on it, but I guess there's good reasons why this is not in the language. Yeah, that's all I have to say.
I would lower this to. I'm kind of prepared to pay whatever cost of maybe. I would just lower this to with P, like lambda that returns, right? Like it feels to me that there's a trivial lowering of this. You just create a function which does with inside. This lowers to a function which inside it does with P return P. Return index plus value. That might lead to some slight weirdness, but I would think that should work.
Thing is, when this is an expression, which precedence should it have? Can you use it inside an operator? Should it be an operator? And all these kind of questions come up then.
Sure, absolutely. Again, like I think it's really nice, and if the only way to make it work was to give it such, give it precedence such that the only real way to ever use it was to put brackets around the expression that you were applying it to, okay, that's fine. I don't mind a couple of extra pairs of parens. It's a lot better than the alternative. So, yeah, that's my view.
Going back a bit to the examples of your range-based language that you've given, one of the things that happens in sort of, I'm going to say workbook-based languages like R and like Mathematica, is that you can see after every step of the transformation that you do what sort of types or what sort of value you're dealing with. How are you dealing with like discoverability of the content of or the type of an expression after each step when you're forming an expression like that?
In truth, not very well, because we haven't really got to the point of implementing really good. So, I mean, if that's a tooling question, that's like reasonably high priority to-do list stuff, like being able to have a little bit of tooling to help. As far as just manual introspection of these things, you can ask what type something is. You can take a look at the first few members. It's not the most convenient way to do things right now, but people do it. They get work done. It's not so bad.
So your analysts write SIL code. Excuse me. Yep. Which is then translated into D.
No, so it's just interpreted. It's an interpreted language, SIL. So the interpreter is written in D, but oh, you mean the workflow aspect of it? You do write the code in SIL and then translate it to D for proper productionizing.
Yes.
A bit of that has happened, simply because we have to. Sometimes things are too slow in SIL, and you have to go to D, or something's just become a bit awkward, and it's easier to do in D. A lot of this has been very responsive to the immediate needs and the sort of time pressures in terms of what's in SIL and what's in D. Yeah, it is absolutely the sort of thing that when something is being developed in SIL and if it's getting a bit out of hand, or it's become important enough that it needs to be taken over by like a serious programming team, you might consider translating. But from my perspective, I would like to have the language good enough that you wouldn't naturally feel the need to have to do that in most code. Like it's very important that it's an option, and the way that we've designed the language kind of makes it possible very easily because most of the functions are the same, right? Yes, a bit sometimes, hopefully not too much.
All right, so these will be the last two questions. Oh, one question.
Any plan of making a Jupyter kernel for SIL and plugging this into Jupyter?
Already got one.
Oh, that's great.
Yeah, that's you can go on, not for the SIL, but you can go look on I think Jupiter Wire. I think it's on the Kaleidos Associates GitHub, which implements the Jupiter protocol, and that enables us to do this. The code that makes a SIL Jupiter kernel actually work is, like, Attila, roughly how many? It's like 100 lines, maybe? Yeah. About 100 lines of code makes it work as a Jupiter notebook, in a Jupiter notebook, yeah.
All right, then that's it. Thanks again.